Up till now, the order in which the data was taken was irrelevant. It doesn't matter which numbers came first and second and third when you're measuring the length of a book. And when you're flipping a coin, it doesn't really matter if I flip one head, whether I got a head first or a tail first, it's still one head. The order in which things were taken really didn't have a whole lot of meaning. However, today's work, there will be a lot of meaning to the time. In fact, to be time series data, data must be taken periodically. It must be taken in time. There must be a time element to it. In fact, we have to take it hourly or daily or weekly or monthly, minutely, secondly, whatever, but it must be taken periodically in time. Now, we've got to be a little lenient with this. For instance, the stock market. You have daily readings of the stock market. But the stock market's closed Saturday and Sunday. So what we have are daily readings, and then on Friday it ends, and Monday is the very next day. There's a 5-day week to the stock market. It's a daily readings, but there's no Saturday and Sunday. It's not as if there's zeros on Saturday and Sunday. There's just no Saturday and Sunday. So the listings would be Monday, Tuesday, Wednesday, Thursday, Friday, Monday, Tuesday, Wednesday, Thursday, Friday, Monday, Tuesday, Wednesday, Thursday, Friday. And that's perfectly all right. They're taken periodically. Every day follows the day before it in the same interval. So first of all, data must be taken periodically. However, this is not enough. It's not enough for data to be taken periodically. If everybody in the class were to come up, we had a great big scale here, and I would weigh everybody, 1 minute per weighing, and I wrote down the weights of everybody, 1 minute. This would be pretty periodic. It would be time data, weight one, and then a minute later, another weight, a minute later. This data would not be time series data. This would simply be random data, just like measuring a book. And it really doesn't matter when I measure the book, and it doesn't really matter when I took people's weights, because those weights would not show any relationship from one to the next. You see, there's no relationship between the weights of the people as they came up. It wasn't as if I put them in size place, just people randomly came up and I weighed them. Well, that data is not time series. Time series data must have something in it that's related to the time. And what it is that's related to the time is one of two properties. Trend, which can be positive or negative, and there's another kind of trend that we'll put down, we're going to get to, seasonal. Seasonal trend, which itself can be positive or negative, and autocorrelation. It's not the same as correlation, but related to it. It's an autocorrelation, and it can be positive or negative. If you have no trends and you have no autocorrelation, even though you've taken things in time, you are not time series data. Okay? So, when do we have time series data? We have time series data when data taken periodically which has at least one of these properties is said to be time series data. Okay? If the data is taken periodically and it has either trend or autocorrelation, it doesn't have to have both, but it can, of course. If it has either trend or autocorrelation or both, then it's considered to be time series data. So let's investigate what we mean by trend or autocorrelation. The first one, trend. Trend can be positive or negative. Let's look at it. We say we have a positive trend if the data seems to be getting bigger in time. Data generally gets bigger as time goes on. Time goes this way. Positive direction for the y-axis is this way. And the data seems to be getting bigger as time goes on. Of course, it'll bounce around a bit, but the data trend tends to be bigger as time gets bigger. That's a positive trend. Positive. If the data tends to get smaller, it's going in the negative direction as the positive time goes positive. As you get more and more time, the value gets lower and lower and lower and lower. Then I have a negative trend. So if generally data is going higher, positive trend. If generally data is going lower, negative trend. If I were measuring my child's weight over the years, the weight would generally get bigger year after year after year, and I'd say the child has a positive trend in his weight. If if my wife were on a diet and she stopped eating all fats and all sugars and things like that, her weight would start dropping, and she'd have a negative trend in weight. Okay? So that's a trend, positive or negative. The second topic that it could have is autocorrelation. Autocorrelation is related to errors. Related to the errors. We'll see how. There can be a positive or a negative autocorrelation. Let's look at what the pictures look like. What happens is the trend, let's say this is the trend line. That's the trend. We know that's the trend. And yet the data seems to bounce. If it gets above the trend line, it stays above the trend line for a while. And then if it gets below the trend line, it stays below the trend line for a while. The errors seem to remember where they were. They have a remembering. Oh, if I got an error here, the next one will be close to it. You can't, if the errors can't change from where they were too much at one time, then there's going to be a positive autocorrelation. So if I'm above average now, I will tend to be above average a moment later. I will tend to be above average the next time and the next time, until if I ever get below average, I will tend to stay below average for a while. So we have this characteristic snaking around, slow snaking around the trend line. This is the trend line, and we slowly moving around it for the real data. That's a positive autocorrelation. The errors are positively related to each other. They remember where they were, and they like to be near where they were before. The other kind of correlation, autocorrelation, is negative. And you'll notice that these are jumping back and forth across the trend line. Here's the trend line, and the errors are above it, then it goes below it. Next one's above it, next one's below it. Next one's above it, next one's below it. They seem to not only remember where they were, but they try and do the opposite of where they were. They negative related to one another. If one's above, the next one will tend to be below. If the next one's below, the next one will tend to be above. Above will then cause a below, below will cause above, and you bounce around feverishly around the trend line. That's a negative autocorrelation. Now, any data which exhibits either a trend or an autocorrelation can be called time series data. Simple. The next kind of trend is a seasonal trend, and we say that it has a seasonal effect. If the data appears to, not the errors in the data, but the data itself over the long haul appears to have a cycle to it like that, the period of the cycle is from this point to the same point. It's starting up here, it's starting up here again. So from here to here is called the period of the cycle of the seasonal effect. And usually the cycle period is about a year. Not about exactly a year. It could be a week, depending on what it is you were doing, but in most economic situations you would find a year. And what happens is you have a seasonal effect. You could also have a trend superimposed on it, which if you had a positive trend, the picture would look like that, and things would be cycling, but generally going up. You could have a negative trend to your seasonal effect, and things could be generally going down, even though they're bouncing up and down all over the place. The tendency would be to go down in effect. The stock market has many, many of these things going on at the same time. Another ingredient, one which is a little troublesome, is called noise. Superimposed on everything you do, there's noise. Now, let's say we had a trend line here, and nothing else, just nothing. In fact, there isn't even any trend. There's no trend. It's not positive or negative. If you shoot a buckshot gun at this thing, you will have data all over the place, and we call that random data. Well, that random data is around this line. Well, if this line were going up, there would be a positive trend, and there would be a random effect around that trend. If we're going down, there'd be a negative effect, but a random trend. And if this line were actually curved because of a season, the effect would be random around the season. Well, we know randomness causes trouble, and we want to get rid of randomness. And how do we get rid of randomness? The age-old trick for getting rid of the random errors, the experimental errors, is to take an average. So what we're going to do in time series is take an average. We're going to average out some data. But we've got to be very careful here. If we just took averages like we did, we would miss seasonal effects, we would miss trends, things would disappear. So what we have to do is, let's draw a picture of it and see. Let's say I had data like this. Now I want to plot something. I want to plot this data. I want to get rid of, obviously there's noise here, and there's some smooth curve through that, and I want to plot a smooth curve through that. Well, instead of this point plotted here, what I do is take the value of this point, the value of this point, the value of this point, and average them up. And I'll get some number, say here. And that's where I put this point. I move to here. Now this point is here, but the points next to it are here and here. If I average up the heights, the y value of this point, and this point, I might get some number, say here. And that's where I'll put that point. This point, I have this point, and this point, average them up. This point is now this point, and this point. This point and the 2 points next to it on each side. Average them up, I get something over here. Take these 3 points, average them up, I get something over here. These 3 points, I get something over here. As you can see, what's going on is that I am smoothing out. I'm putting a curve through those x's and smoothing out the data. I am estimating the mean of the data, which is getting rid of the noise. This is called a moving average. So if I have a moving average, because the average is at a point but on 2 sides of it, and then I move to the next, and I move to the next, and I move around. It's called a moving average. It's very easy to do. Algebraically, all we have to do is do it. And let's see what happens when we have a picture. If we had a picture something like this, and we did a smoothing, a moving average, the points would just fall right smack in the middle, and I would have a sketch like that, and it would be a lot cleaner. The errors would sort of disappear. So if I had nice errors like that, they would disappear using a moving average. So let's see how we do a moving average. Pretty easy. Moving averages are kind of trivial. You have the numbers x1, x2, x3. These are the heights at time 0, 1, 2, 3, and so on. Well, we don't plot anything at the first x. For the second, at the first x, so I'm calling x0. The very first x, which is the second x in my chart, I'm going to put something at that point, but I'm not going to put it at the height x. I'm going to take x0, x1, and x2, that is x1 with the things on both sides of it, add them up and divide by 3. That will give me an average. I'll call that y, and I'll plot y instead of x. So that's the average of x1 and the 2 x's on the 2 sides of it. For x2, I'll take x2, average it with x1 and x3. Add them up, divide by 3. And I'll use y instead of x. I'll put this on my chart. For x3, I'll replace with y3, which is the average of x2 and x4. And this continues on to the next page. In x4, I will put x3 and x5, average with x4. This is a straightforward moving average. And of course, the very last point, there's nothing you can put on in its place because there's no x9. And that will smooth out the errors, and I'll be able to see what the season looks like, what the trends look like, a lot easier because the noise will be averaged out. Okay? That's time series. It's very useful in analyzing things that are definitely a function of time rather than things which are just random errors. Have a